So when you take a look at light, they decided that light was a wave and not a particle. Because when you confine light to a little hole, it expands and gets bigger, it diffracts. And they also determined that light was a wave because when you shine light through a dual slit, just like this, you'll get a diffraction, you'll get an interference pattern just like this. So light interferes with itself the way a wave needs to. So you add those pieces of evidence along with the fact that they believe that to increase the energy in waves, you increase the amplitude. And they have all these qualities and they've decided that light is a wave. Well, the very notion that light is a wave was eventually challenged by a man by the name of Max Planck. He was shooting light at what's called an electroscope, and let's just say a plate. And something he noticed was that no matter how high the amplitude of the light, nothing happened. But if he changed the frequency, if he increased the frequency, electrons would jump off of that plate. Another word for the plate is electroscope. So if he had a high frequency light, which according to the general wave rule has low energy, it knocked electrons off. But if you had high amplitude light, there wasn't enough energy to knock electrons off. So they end up in this situation where they're not sure what to think. Because they thought to themselves, if light is a wave, that high amplitude or high energy should have enough energy to knock electrons off. The low frequency should not, but it was the exact opposite. And so this really, really baffled scientists, and they weren't sure how to perceive this. And this is one of the many genius things that Albert Einstein came up with. He said, what if light is both a particle and a wave? And he came up with the idea of wave-particle duality. And he said, light is a wave, but it's a different kind of wave. Instead of its energy increasing with amplitude, light's energy increases with frequency. And light is also a particle because you can narrow light down to little particles called photons, which are massless but have energy. And photons have this wave-particle duality. They're both particles and waves because they have these characteristics of interference and stuff, but you can break them down to a single particle. Now, the really interesting thing about photons that was able to add credence to the wave-particle duality, if you break down light into photons, it will still interfere with itself. So if you imagine you've got a single photon and you shoot it through a double slit, it'll form an interference pattern. So even when light comes through a double slit, one photon at a time, it still interferes with itself. And so to kind of give you an example, imagine throwing a tennis ball through a double slit, and all of a sudden it forms this kind of interference pattern on a wall behind it. That is what was happening with photons. So photons, even though they're particles, they distribute the interference pattern even when they're fired one at a time. And so that added to the wave-particle duality. So there's a few things you need to remember. Number one, to increase the energy in a sound wave, you increase the amplitude. But to increase the energy in a photon, you increase the frequency. So light waves and sound waves have a very inverse relationship. And this right here, this diagram right here, is to help you understand how waves work. So right here down at the bottom, we've got low frequency, high amplitude. Up here at the top, we've got high frequency, low amplitude. Radio, micro, infrared, visible light, ultraviolet, X-rays, and gammas. So there's lots of little things you can do to memorize that, but just make sure you have that memorized in order with highest amplitude, highest frequency. But other than that, I just want to end this by saying the proper response to when somebody asks the question, is light a wave or a particle, is yes. It has wave-particle duality. It distributes characteristics of both waves and particles.